Let's take a look at the mathematics of torque, the cross product and rotation, and how they apply in real scenarios with real tools. If you're using this video for a review, feel free to scan through and only watch, rewatch, and copy the parts you need. However, if you're seeing this for the first time, feel free to take comprehensive notes and write down what we say and talk about in addition to anything that might be on the screen. Let's first start by reviewing the cross product as we've learned it in math class with vectors. Torque fundamentally is a cross product. It's the best example of a cross product in the real world because this is what cross products do. If vectors are at cross purposes to each other, one of them will cause the other one to start spinning. The cross product in math gives specific instructions with two vectors. It says to multiply the perpendicular bits. Last semester when we were studying work and energy, we did the dot product. We said there's the force, there's the displacement, and look, if you want something to move this way, you're going to have to push this way. If you want something to move that way, you're going to have to push that way, not this way. We want to multiply the perpendicular bits. We set this up as a right triangle. This is the opposite. This is the adjacent. Adjacent means cosine. So the parallel component B that we're going to call x here on this side, that's going to be b cosine theta. And the dot product we said was ab cosine theta. That gives you your work. It changes your energy because you're pushing in the right direction. Now we want to do the opposite. We want to multiply the perpendicular bits. Here's B. B is mostly perpendicular to A, but not fully. This does not look anywhere near a right angle to me. This looks more in the 70 degrees. The perpendicular component of B is here. There's that nice right triangle again. Let's see which side is the... Say it out loud. Say it. Say it. Opposite. Opposite is. Opposite is sine. This here. Sine theta is y over b. That means that this component, the perpendicular component, is b sine theta. Cross product says I want to multiply A and the perpendicular component of B. When you're taking a cross product, look at A and B. If they're perpendicular, work is done. Cross product is A times B. If they're not perpendicular, multiply A by the part of B that is perpendicular, namely B sine theta. Any cross product anywhere, ever, if you want a plain numerical answer, aka the magnitude, A cross B is AB sine theta. That's right, it's A cross B. Don't say A times B. Times is meaningless to vectors. You can't times a direction by another direction. You can take the dot product, which means multiply the parallel bits, or take the cross product, which means multiply the perpendicular bits. If you do that, you'll get an answer of first vector times second vector times the sine of the angle between them. Notice that theta is the angle between them when they are drawn tail to tail. Cover your picture with diagrams until the two vectors are drawn tail to tail. If you have one arrow anywhere near another arrow, if you have tip to tail over here, stop, redraw your picture. We're halfway done. The cross product is also known as the vector product. Unlike energy, which is a scalar and has no direction, either you burn 100 calories or you don't. You don't burn it differently by running south instead of north. The cross product is definitionally a vector product. The direction of A cross B, that cross product, is perpendicular to both vectors. Taking notes? Good. Look at A and B as drawn on your notebook in front of you flat on the table. Now take your pencil and demarcate with your pencil, you'll need your pencil, the directions perpendicular to both vectors. Pause. Press play to check your work. Ready? Check it out. Can't write? Of course you can't write. Your pencil's in the air. The only direction that's perpendicular both to A and B on your page is with your pencil pointing straight up out of the page at your nose or possibly straight down into your desk. That's the direction of the cross product. The cross product is definitionally 3D. That's why you learned about it at this weird wonk place in your pre-calc curriculum that had nothing to do with anything because they needed to wait until you'd learn how to deal with three-dimensional vectors. By definition, if you've got two things and a third one that's perpendicular, something is going to be sticking out of your page. Resign yourself never to being able to draw this nicely. That's okay. This is physics class, not art class. Let's take a look at what this means. The direction of the vector cross product was not just invented to give math students a headache. The direction of the cross product tells you fundamentally which way the wheel is spinning. Here's a wheel. Which way is it spinning? Say it out loud. How many people said clockwise? Great. Clockwise it is. First problem, look at it from below. It won't be clockwise, it'll be counterclockwise, but it'll be the same wheel spinning in the same direction. It's our first indication that clockwise and counterclockwise are not useful directions to be giving pilots, engineers, and anybody else who want to build or drive something that you don't want to crash. Second problem, this wheel's spinning clockwise. Let's make sure that we're looking at it from above. Oh, what was that? Oh, what was that? Notice that by our definition of clockwise, the wheel was spinning clockwise the whole time, even when it went off balance, even when it fell off completely. Let me tell you, if this is a vehicle I was riding on, I would want the physics to warn me if the wheel was going to do that. And I would want an engineer to put the wheel back on. That wheel completely fell off and rolled away. And the fact that it is still spinning clockwise does not mean the wheel didn't change correct direction. The direction of the vector cross product tells you the only direction you really need to know, and that direction is not clockwise, it's where you put the axle. We want this wheel to stay on its bearings on a vertical axis of rotation the whole time. If it tips, that axis of rotation tips to the diagonal. That is bad. We want to know about it. We want to fix it. If it flips upside down, the axis of rotation flips from up to down to up, and we know the flip has been 180 degrees of upside down. Now, let's talk about the right-hand rule. We can clearly tell the difference between up and sideways. Let's make sure we can tell the difference between an axle that's pointing up and an axle that's pointing down. There is our right-hand rule. There is our vector definition as ever before. If we wanted to spin vectors A and B around a common axis of rotation, it would look exactly like our definition from before. The direction of the vector cross product is along the axis of rotation, and that axis of rotation is perpendicular to both vectors. How do we tell the difference between positive and negative? Take out your perpendicularometer, aka your right hand. If you're right-handed, put your pencil down. If you're left-handed, this is the one time the universe works in your favor. Keep writing. Set up your perpendicularometer, first 3 fingers of your hand, all perpendicular to each other. Pointer finger, first vector. Middle finger, second vector. Answer, your thumb. Keep them all perpendicular. Twist your hand. Yeah, I know it's going to be a little bit annoying. Make sure the pointer finger of your right hand is going to the right. You'll see vector B going into the page and your answer pointing straight up. Up is positive, down is negative. Right is positive, left is negative, forwards is positive, backwards is negative. Same sign convention we've been using in math class since 7th grade. We're not going to mess with it now. If you can do that without spraining your thumb or breaking your wrist, you will always know where to put the axle, the direction of the torque as per the right-hand rule. If this is a pain in the butt, or at least a pain in the wrist, use the curl Luke. There is a simpler, more comfortable version of the right-hand rule where you can clearly see which way the wheel or the gear or the whatever it is spinning. Curl your fingers around the direction that the wheel is spinning. Make that nice clockwise. No, not counterclockwise. I see you there. That is counterclockwise. Look at your fingers. Twist, twist. Yeah, I know. Try it with your elbow up. No, your elbow's down now. Try it with your elbow up. Got it? Got it? Fingers curling clockwise? Which way's your thumb pointing? Aha! Your thumb is pointing down. That would be negative. That means this axis of rotation here is not pointing up, it's pointing down. Notice that we are using the same sign convention that math classes always used, and we can use it here after without necessarily breaking our wrists on the right-hand rule. We see this. This wheel is turning clockwise. Clockwise is negative. Counterclockwise is positive. Axis of rotation, up and down. Which one is it, up or down? This is rotating clockwise. That would be down. That would be negative. Now let's take a look at this on a real torque wrench. Here's the torque wrench. We want to turn it like this. Pull. In order to get something that's at rest turning, we need to apply a torque. Formula for our torque is F cross R. We want to take F, the force we need. We want to take R, the radial distance between where we're pulling and the axis of rotation. Multiply the perpendicular bits. There's F. We're pulling. You can see the direction that the hand is pulling. There is R. Start at the hand and go in to the axis of rotation. That is your vector to label it. We're going to need it. Check. Are they perpendicular? If so, if you're pulling at 90 degrees, great. Multiply FR, check your units, and done. I'm looking at that picture. That does not look like a 90-degree angle to me. So check R is clearly the length of the handle of the wrench. We're going to need it. And the angle between them looks like about 140 degrees to me. All right, F cross R, they're not perpendicular. That's going to need to be F R, that's the length of the whole handle. Now we'll round and assume the bolt's kind of small, times sine of theta. Let's say we're pulling with 100 newtons of force, and it's a 10 centimeter handle. Check your units. We need newtons, we need meters. Plug it in, press pause, press play to check your work. Ready? If you're getting a torque of about 6.2-ish Newton cross meters, there's the unit force, newtons times meters, then you are in good shape and you are exactly halfway done. This is the torque we'd be applying to this torque wrench to start it turning just like in the animation. Now we need to put a direction on that. We are not quite done. Direction of the cross product is perpendicular to both vectors. Right-hand rule goes ow, so let's take a look at the picture. Clearly, where you put the axle, we can see the axle with our very own eyes. Yep, same direction as our old right-hand rule gave us. It is right over here. In it? Oh, possibly it's here. How can we tell? All right, take your fingers, curl them in the direction that the torque wrench is going to turn. Looks to me very, very much like clockwise. Clockwise is negative. That is clearly down rather than up. Clockwise around the vertical axis. Email me or take notes or both if you have questions about this example. What good does 6.24 Newton meters of torque do us? I don't know. We're not done yet. We actually haven't gotten it moving. We've just said what we intend to do. Now, here's where we apply Newton's second law for rotation. Newton's second law last semester said one force equals mass times acceleration. That is, to get something moving, you need a force. If you don't have a net force, it's going to sit there doing nothing, or sit there moving in the same direction and speed that it was already moving. How did we get there? We needed to know mass, aka how hard it is to move, and multiply by acceleration, aka how fast you got it speeding up. Rotation works the exact same way. If you don't want something at equilibrium, if you want it to start rotating, or if it's already moving and you want it to stop rotating, you need a net torque. That torque will depend on how hard it is to, well, not move, but rotate, and the effect will be the same. How fast its rotation speeds up. How hard it is to rotate, spin, topple, or turn. Hey, that sounds like rotational inertia, or moment of inertia. How fast its rotation speeds up. Well, this was regular acceleration. That sounds very much like angular acceleration. Newton's second law for rotation. Write it down. Put a box around it. A torque is caused by moment of inertia and causes an angular acceleration. Equilibrium now means also no net torque. You won't start spinning. Now all we need to do is check the shape that we have and see if we can look up the moment of inertia in one of those handy charts. Here's our problem. What shape is this? Basically, we are assuming that this works the way the black bar does, plus or minus a bolt on the end. Look up this shape and the way it's going to rotate on your chart. Press play when you're ready. Ready? Basically, this shape, plus or minus your hand and the bolt, is a long rod pivoted about one end. If you looked up 1/12 ml squared, that's a rod being twirled like a baton twirler about one middle. And I don't think that's what we want to do with our torque wrench, at least if we're not using it to lead a parade. Now, angular acceleration, rearrange, is torque over moment of inertia. We got the moment of inertia. We even got the torque from the last problem. It's FL sine theta. Plug both in. Simplify as far as you can to get a formula in letters for the torque wrench problem. Press play to check your work. Ready? There we go. Cancel out one of those L's. Move the 3 up top, and we got a nice little angular acceleration. Direction, as we said before. There is our axis of rotation. Clockwise means down, same as it was before. And that is how fast the tool is actually going to start to rotate in your hand for all that pulling. Now we're done.